I am now starting the last chapter of Module 4, which is Chapter 22, which talks about some program development tools. So, when we say we have some programs, to execute those programs, we have some tools, or there are some necessary tools that are built in inside the system for us to execute those programs. So there are various steps in execution of a program. First is to write a program, then you compile it, then you run it. So when you say you're compiling, you're running, there are multiple steps that are happening internally, like linking, loading, and conversion of files from human understandable language to machine understandable language, and again reconversion from machine language to human language, human understandable language. So firstly, let's see how we can handle multi-source C applications. So first, we are only referring to C programs. Then we'll say that they are also applicable to programs in all languages. So usually what happens when I have a C program, once I compile it and run it, the output file is usually of the form a.out. So what are the steps that happen in between a file having an extension .c to .out? So the standard technique of using cc foo.c. So here foo.c is a C program. To create the a.out executable needs to be modified when working with multi-source programs. That means so far whatever we have done, whatever programs you have executed may have only one source file. That means I'm using one file and I'm trying to convert or check the output of that. Let's say a basic C program to find the sum of two numbers. There is only one source file there. What happens if there are multiple source files? What happens if a project has three modules and those three modules are three separate C files or three separate Python files? How are they going to be interlinked together, and how are they going to be converted into machine understandable language, and how are they going to be executed? So three phases of a C program has to pass through Three phases a C program has to pass through before a standalone executable is created are compiling, assembling, and linking. So what is compiling? Compiling converts the C source code, that is whatever program that we have in the extension of .c, to assembly level language. So what is assembly? You have an assembler inside your system which converts it into the machine understandable form. So what does this assembler do? The assembled code is transformed into object code by the assembler. So your source file in the form of .c is converted to an object file of the extension .o. So the machine understands this code, but it cannot be executed directly as it is incomplete. So it is just going to compile, or it is just going to translate some part of your program into machine understandable language. Not everything has been translated. So it does not include the code functions used in the program. So when does that happen? The step that happens there is called as linking. The object code of the program is finally linked by the linker or loader with other object files and libraries that contain code used by functions. So we have certain built-in functions and they are associated with some libraries. So all that is done by the linker, or that step is called as linking. Now, once the compiling and the linking is done, you get an executable file which is by default of the type a.out. So if you remember, we do it as ./a.out. This gives us a generic form or a default form of a.out. You can use, or you can create an output file of your choice while you perform the compiling step as well. I think some of you know that. Otherwise, a.out is a default output or default executable file that is generated when you run your program. So now usually what happens if we have one program, let's say I have a C file, and it is always understood that if I make any change in that single C program, I have to recompile it for me to get the correct output. So let's say I have typed a program, I have made a mistake or there's an error in that program. If I go back to the program and correct it, it is mandatory for me to recompile that program to observe the changes that have been made in the original file. The same thing applies here as well. Only difference is you have to understand that there need not be only one source file. You can have multiple source files. Like I said, you can have one big project in the form of 5 different programs. So all 5 programs have to be interlinked together, or they have to be compliant with each other for your project to work in a proper way. So what happens if I have multiple files, and how do I keep them up to date? So there is one command called as the make command, which is used to keep programs up to date. So let's assume that the files in the sample application are related to one another. So there are 2 files here, quit.c and quit.h. Okay, and quit.o depends on quit.c and quit.h. True, if I have 2 files, quit.c and quit.h, when I compile, I'm going to get an object file of the type quit.o. So if I make any change to quit.c or quit.h, I have to recompile it and recreate this file quit.o. I hope you are all following. So quit.o depends on quit.c and quit.h, and if either of them are modified, then quit.c has to be recompiled to recreate quit.o. This is already a built-in file, or it contains some functions. Quit.c is my original source code. So if I make any changes to these 2 files, I have to recompile them to recreate this. So there's a problem here. How many times can I keep going on doing this? So what is the solution for me to reduce my job here? So assume that there is another file rec.o that depends on quit.o, which means that it needs to be rebuilt as well. So let's say I have quit.c, quit.h and rec.o. Now this rec.o, we know that quit.o depends on quit.c and quit.h. Now we have another file rec.o that depends on quit.o. That means you have to rebuild quit.o as well, because they are all dependent on each other. So what is the problem here? If I have hundreds or thousands of files like this, keeping track of those dependencies is difficult. So keeping track of these dependencies in a large application involving several dozen files is simply impossible without a tool to assist us. So if we don't have a tool, we won't know which file is dependent on what, and where, if we make a change, what is going to be reflected. So the make command handles this job very well. How does it handle it? We'll see what happens. It shortens the program compilation time by recompiling only those sources that have changed. So it understands that what is the source file that has changed. So only compiles those files and does not unnecessarily repeatedly compiles the other programs that have not been modified. That is the most important advantage of this make command. It looks up a make file that specifies two things. So there's something called as a make file that is created when you use this command make. So what are those two things? How a program or object file has dependencies on other files. So what is the dependency that is there? Then the command to execute when a file on which another file depends changes. This could be to run the cc command to regenerate the object files. So one, it will check for the dependencies, and the second is to execute when a file on which another file depends changes. So make by default uses a file named makefile or makefile in the user's current directory. So here it can be either a lowercase m or an uppercase m. This file contains a set of rules where each rule is of the form target, dependency list, and command list. So please note there is a tab specified here. So there is a target. There are some files that are dependent. So they are specified in the dependency list. And then there is a command list. Here, target is generally an executable or an object file. So this can be any .out file or .a file, which depends on the dependency list. If any of the files in this list change, then the target has to be rebuilt using commands provided in the command list. So if I make any change in this list of files, then I make use of these commands and recompile or recreate this target file. The rule syntax is simple, except that you need to keep in mind that the command list is preceded by a tab. I repeat this. So in this case, I have a target, I have a dependency list, and I have a command list. So this target can be any output file or it can be an object file. And dependency list is a list of files that are dependent on this file of target. And command list is a list of commands that have to be executed if there is any change in the dependency list. And always provide a tab before your command list. So let's see an example here. Like I said, I have the target, dependency list, and the command to be executed. So the make rule for quit.o is this. That means quit.o, what are the files that are dependent? Quit.c and quit.h. And what is the command to be executed if I make any change here? The compiling command. cc -c quit.c. Make monitors the modification of all the three files, and when it sees at least one file in the dependency list to be newer than the target, it runs cc -c quit.c to recreate quit.o. So in this case, there are two files. It will run both the files. If there is any modification done here, then it has to rerun this file quit.c. Make, so like I said, make is not restricted only to handle C programs. It can compile any program written in any language, provided the compilation generates target files that can be compared to their sources. So it has to be compatible with the compiler and the target files that have been created. Why do we have this make command, and what happens with the usage of this? So the make file, so we have removing redundancy. Redundancy means duplicates, or redundant copies means duplicate copies. Unnecessarily, we might have multiple copies, or we might be performing the step unnecessarily repeatedly. How can we avoid that? So the make file we worked upon has a number of redundancies, and Make is provided with a fair amount of intelligence to make the deductions. So how can we stop by unnecessarily compiling those files which we have not made any modification? There is no point in compiling them again and again. If the target and dependency have the same base name, the command list need not be specified. So if I have quit.o, quit.c and quit.h, the base name is quit in all the three cases. So if I have the base name same, quit, 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 then I do not have to specify the command list. So if the target and dependency have the same base name, the command list need not be specified. In other words, quit.c has quit.o has quit.c and quit.h as its dependency, then you do not specify or you don't need to specify cc minus c quit.c. That means no command list is required. If you remember, base name is the name that is to the left of the extension. If the source file itself is omitted in the dependency, if the source file itself is omitted in the dependency, make assumes that the base source file name is the same as the object file. So here I have not specified the source file. Quit.c is the source file. If I do not specify that, so if you see, I have reduced from the previous line where I had so much to just one line. Why? That is what I'm saying. If the source file itself is omitted in the dependency, make assumes that the base source file name is same as the object file. So if I omit this, then I can just specify the object file and the other file. So the above line thus gets shortened. So I have tried to simplify a two-line code into a single line code. What are the other functions of make? That is cleaning and backup. So we have seen what is backup. If I have certain files, if I am afraid that I am going to lose them, then I can create a backup using TAR command, if you remember in the previous chapter we have studied. Same way here. Make does not always need a dependency to work on. It can run a Unix command depending on the command line argument. You can instruct make to remove all object files or even perform a backup with tar. Suppose I want to remove all files with the extension .o or perform a backup. Then I can use the tar command, TAR. The make clean command is often run at the beginning to remove all object files in the current directory. So let's say I'm making use of a project and every day someone has been adding something to those source files there. So every time, I don't know if you have a practice of doing this, every time you try and code a part of your problem, you compile it to see that at least that part is working. So there is an object file created. So usually when do we clean those object files? When I want to recompile them. Instead of keeping multiple copies, I may want to clean it once before creating another one. So the make clean command is often run at the beginning to remove all objects. That means clear all the object files in the current directory. So once I have cleared them, obviously it means that I have made some modification and I want to recompile. So this is followed by a regular make to force compilation of all programs, just to see if there has been any modification done and if there are any errors. So what are these macros? Macros, I think you would have studied in microprocessor, where if I have a certain number of steps that are to be performed repeatedly, I'm going to save those multiple lines as one macro. And I'm going to specify that macro name. When I specify that macro name and call it, it is going to substitute all the lines that you have defined for that macro instead of repeatedly using them in your program and increasing the length of your program. Make supports macros, sometimes called variables, that are used to define repeatedly using strings. A macro is of the form macro name is equal to value and is defined at the beginning of the make file. Usually macros are defined in the beginning of the program. A macro is invoked in a rule with $macro name or inside flower brackets. It is either specified in parentheses or inside flower brackets. Even though we have used the CC compiler here, some systems may instead use GNU's GCC. That is GCC compiler. Instead of CC, it might use GCC. To be able to run the same make file on another system that uses GCC and without major changes in the body of the make file, we define a macro CC is equal to GCC. That means your set of code has to be compliant with all different kinds of systems. So to make it compatible with an example here with GCC compiler and CC compiler, you'll have to include a macro CC is equal to GCC. I'll show you an example of how macro works. So here I have make file 3. This is my file name and I'm trying to write the program here itself. You need not know this code by heart. You just have to understand what is happening here. So what I'm trying to do is I have initialized CC is equal to GCC. That means I'm trying to say that whatever works on CC compiler must also work on the GCC compiler. So CC is also a macro. Remember, all macros are put in uppercase characters. Now I have another macro called as sources, which is trying to tell that all these are source files. So I have another file called rec.deposit.c, arg_check.c, and quit.c. So all source files have the extension .c. All object files have the extension .o. So I am just creating a macro called as sources, which will be later when I use it in my program. This sources is going to be replaced by all these files that are there. So it is a tedious task for me to keep on putting this line here in multiple places. So instead of that, it's like a substitute. So let's say I have we had solved problems in logic truth tables, true or false, tautology, logical expressions. So in that case, if I had a big expression like A or B and C, not D, and F. So if there was a big expression, what we would do, we would simplify the first half of it and simply replace it with another letter Q, and then we would do Q or C. So we know that what is that Q? Q is actually the evaluation of the first part of that equation. So same way, it's not exactly the same, but you can just relate it that way. So instead of putting this entire line everywhere, I am just going to define these macros as sources, objects, and headers. So if I say rec_deposit, so this is of the form target, dependency list, and command list. So target is rec_deposit. What is the dependency list? It says objects. So what are the objects that we have? They are all these .o files. And what is the compilation step or the command list? It is cc. So cc will be replaced with gcc, and again objects will be replaced with all o files. So the same thing here. Headers will be replaced by all the files that have extension .h that have been defined here. So basically macros are also used to simplify your program and avoid redundancy. So one of the four macros defines the compiler, and the other three group all files into three categories. So we had CC, source file, object file, and header files. Apart from CC, there are two macros that are built into make: C flags and LD flags. C flags list the options that have to be additionally used in compilation, and LD flags determine the options to be used by the linker. So you have C for compiling and L for linking. Then the last topic is building a library. So you might have seen this in different applications. It is included in WhatsApp as well now. Archiving our files. So they are basically grouping files into one category. So it is indicated by AR command. In real life projects, specifying all object files in a make file can be a tedious job. So you might have thousands of object files. So grouping them can be a difficult job. So how can you do that? It is more convenient to group them into a library or archive them with that AR command. So when I say I'm grouping them, I have to create an archive and it has the extension .a. Now, when I say I'm grouping them into a library, I have different options that I can use along with the AR command. So the first one is -r. Remember, it has to be used with AR command. AR -r adds a file if it is not present in the archive or replaces an existing one. R stands for replace. -q appends a file at the end of the archive. -x extracts a file from the archive. -b deletes a file in the archive. -t displays table of contents, and -v stands for verbose output. That means if you want an explanation to be given along with your archive when it displays what are the contents of the library, then you can use -v. This completes module 4, chapter 22.